area of our session, which is exploration concepts, instrumentation, and monitoring of small bodies. So if anybody has thoughts to bring up about that, now's the time. Derek?
I'll take it home with me. A thought about ARM. If we use fireball observations, then, and we use the usual methods of interpreting the fireball and the breakup and so on and so forth, objects entering the Earth's atmosphere are exceedingly fragile. Just tiny touches and they will disintegrate. If, and it's a big if, we can extrapolate to the boulders that are lying around on the surface of an asteroid, then the prediction I would make would be the minute you try and clasp that thing, it would disintegrate. Now, if I'm wrong, and you pick it up, and you spend 6 months taking it back to a lunar orbit, and then the astronauts arrive, and then it disintegrates, you mess up both the robotic spacecraft and the human spacecraft, the crewed spacecraft. So I would think the first thing you want to do when you see that boulder sitting there on the surface is whack the hell out of it. Put it through as rigorous a mechanical test as you can with that robotic spacecraft, maybe even possibly jeopardizing the spacecraft, but you really beat on it before you risk carrying it for 6 months back or 12 months back to the lunar orbit.
That's an interesting approach. Right now, based on the meteoritic samples and our understanding and observations based on Hayabusa, the boulders appear to be coherent bodies, at least on S-type. We'll know more when we go to Bennu and Ryugu, but the danger there is if you hit it too hard and you exceed the strength of the boulder, then you don't have a boulder to pick up. So
but it's better it disintegrates with no humans around.
Yeah, I think based on the operations, the mechanical operations, and the time, I think we will have a good idea. We have lots of force feedback in the restraint system, and when we bring that boulder in, we will have a good idea of its structural integrity as well as the density, the mass, while we're still in orbit before we do the planetary defense demonstration. If it truly is highly friable, then we'll know that on the first capture attempt, and we have multiple capture attempts. So that will also dictate, do we go for the same size boulder? If we were unsuccessful, do we go to a smaller boulder, which can alleviate some of those concerns? But I'll also let Dan and Paul chime in on that.
Well, there's a couple of things. I think the advent of Phil's network is going to be a huge boon for this question, because basically what you're going to see is material that are in the meter size range at the top of the atmosphere, them interacting with the atmosphere producing some level of stress on them, and they either make it to the ground as coherent objects or they fall apart, and you get, well, if they fall apart and produce a shower, that's a good data point too. I was curious about this because I was on the FAST, and we had a long discussion about what are the strength of things. So I got one of my students to go through the entire catalog of meteorites, looking for things that are boulder size at the top of the atmosphere, so something that's recovered mass of 10 kilos or more. And what's the ratio of showers to non-showers in the meteorite fall collection? And there was something like 270 events. And it turns out that showers are only about a third, a little more than a third of all these fall events. So actually that surprised me a lot. I thought showers were far more prevalent. And this is a very biased sample. In so many ways, I could spend half an hour talking about the biases.
Let's do that.
But still, this is the data we have. And I would have expected that showers would have been far more prevalent than boulders, or or recovered cobbles, and they're not.
Paul, do you want to? Go ahead, Derek.
And there's a poster, poster in the other room.
I think we have to
about
be careful not to mix up lots of different things. I mean, the number of rocks that reach the surface as single rocks and the number of rocks that reach the surface as multiple fragments is one thing.
Yeah.
What we're really worried about here is what was the object like at the moment it entered the atmosphere. And you don't know that from the rocks that reach the surface, because most of these things don't reach the surface. So if you look at Popova et al., 2011, I think it is, maybe 13, she looked at the fragmentation. We've now got 19 meteorites for which we've got video records of the entry. So this is where you get your data from. So if you look at those objects and you determine from the behavior of the fireball the mechanical strength of the object, it is something on the order of 10 to minus 4, 10 to minus 5 of the strength of the meteorites we have in our museums. In other words, what we're receiving...
In some cases, I've looked at that very carefully, and there are quite a few differences, and it depends very much on the material properties of the stuff.
At the point it enters the atmosphere?
Yes.
Not when it's in our museums?
Well, yes. But the stuff that's in our museums still tells us something about the structure and the strength of the boulders.
Of the tough stuff that gets through the atmosphere?
Well, things like Orgay and Tagish Lake are hardly tough.
We don't know what entered the atmosphere in the case of Orgay.
Well, we have video of Tagish
Take
Lake.
Tagish Lake, about 1% of it reached the surface, most of it...
Yes, well, that's the story with all of this stuff,
Right,
is
but
that
the
best
point is,
you get 15%.
How do you take your knowledge of that object as it entered the atmosphere and relate it to ours?
Well,
And
that's why we have this fireball network. That will give us a lot more data. And also, the thing is that there's a lot of data that we don't know. But we shouldn't ignore the stuff that we have sitting around staring us in the face, which is in the meteorite collection.
The problem is determining its relevance.
Well,
Yeah, Derek,
yeah, there are caveats.
Derek, I think your point's well taken, but in the meantime, before ARM, we'll have a Hayabusa 2 an impact experiment on a C-type body. So I'll be just one experiment, but it will start addressing stuff like that as well.
Yeah, and also, Derek, in the collisional process by which the smaller near-Earth asteroids are generated, there's a tremendous amount of energy, force that is applied, and what we see on every asteroid that we've gone to is coherent boulders on the surface. Now, if they truly just fall apart, then natural forces would probably reduce them all to regolith very, very quickly in terms of the thermal properties.
That is happening. All these asteroids have very thick regoliths. That is happening.
Sure, it's happening, but we also see 10 on Itokawa. We see a 30-meter boulder sitting on the surface.
I agree, but we've no idea what its friability is.
Granted, yes, but what I'm saying is if there isn't some inherent integrity structure to it, I venture to say we would see a lot less boulders on these asteroids.
I don't know that.
Well, I think that's
I think that's one of the exciting things we have to learn about near-Earth asteroids as soon as we start exploring them.
Yeah, and let me just say also, if it turns out that all of these asteroids that we go to are so friable that we can't interact with them, that's valuable information if we actually find that out. My gut feeling is that will not be the case.
No, I agree entirely. The issue is, are we going to put the astronauts at risk?
Yeah, no, I think, again, with ARM, we're going to take all of the precautions, and this is one of the discussions in the FAST in terms of containment and pre-ARCM observations and testing. We're going to maximize that to the greatest extent possible. We're going to have 2 years of return trip with the boulder in tow. So we're going to have a lot of time to see how that boulder reacts under strain, under containment. We're going to have a load on the boulder itself, a preload from the constraint system.
I guess I'm just suggesting that during that, I didn't realize it was as much as 2 years, but during that period, we torture the object so that we know it's not going to do anything we don't want it to do when we get people up there.
Yeah, that's a good thought. It's a fine line between doing enough and doing too much, though. So, go ahead, Paul.
So just to address your concern about the astronaut hazard, or the hazard to astronauts, we are going to have a lot of time. I only had 10 minutes, so I couldn't go into the whole operations, but there's going to be, on the way back, there's going to be a chance for looking at the boulder, sort of getting an assessment of the boulder, not only for where we might do the operations, the EVA and things like that, but if there are any hazards and things that we may have to address. So I think that we are going to be very, very sure before we send our crew up there and to interact with it on an EVA exactly what we're going to have and what they're going to expect to deal with. So I think from a hazard point of view, I think we can address that. Certainly if it looks like it's going to be interesting, which I'm not so sure it will be, we won't send the crew out. But I'm almost entirely sure in terms of what we know about the range of types of materials and things like that, it's not going to be a hazard to the crew.
Go ahead.
Yeah, so this sort of shifts gears a lot, but we were discussing the ownership of meteorite falls in Australia, and it inspired in me a question of the international laws that govern the collection or alteration of the orbit of the asteroid redirect mission object. Is there like a firm regime of laws that cover that, or is it all very, we do like we want?
It's not clear cut. It depends upon interpretation of laws as well. But there's precedent. We have precedent of recovering samples from the moon and bringing those back, and so there is precedent. We're just potentially bringing back something a little bit larger than has been done before. Basically, if you interpret, and I'm not a lawyer, but you interpret the current existing international laws, it talks about celestial bodies. And so you have to go into the definition of what is a celestial body. And the intent, I believe, was the moon, the planets, and potentially asteroids and comets taken as a whole. You could extend it to that. But when you bring back part of something, does that make it a celestial body is kind of the legal question. And I don't think it is. And I think we have the precedent that we've done it before. It's a big sample.
Yeah.
But that's my personal opinion. I'm not speaking on behalf of NASA or any other government agency.
So my point of view is it's just a very large sample return. And we have a lot of samples from the moon at Johnson Space Center, and we're just going to have a lot more sample with ARM. So it's just a big sample.
Yeah.
I've been interested in this for a while because it's how do you take a science and make the policy? And you're right at this point. So the Outer Space Treaty is for exploration and use. All of us are involved in exploration. Planetary protection talks about no harmful contamination, so we're doing it while we explore. And right now, there's some big gaps out there. First of all, NASA has turned over, within NASA, not internationally, but we have moved and said commercial, go from FAA launch approvals. So that's different right there. But as far as the part that's exploration and use, that use part has not been defined. So it's kind of a large area where there are gaps. It's not a problem, but that the policy isn't even set at the international level. And the issue, so the US this year and Luxembourg both said that they passed laws that gave commercial users the right to claim something. And so even in the law of the sea, for instance, there are regulations on who owns what territorial waters and things like that. But you can claim and take a fish. You're taking a resource that doesn't give you sovereignty, that doesn't give you any kind of major use over everything. So, and right now what they're looking at is even questions about the deep seabed. Do you, if a commercial user wanted to go down and take off one of those deep sea vent chimneys, is that okay? The scientists think of those as, oh, you should be protecting that. Those resources down there are really important, but that's also biominerals, and they have the right to use it. So these are places where there's a lot of legal ambiguity, and the International Institute of Space Law is looking at a number of these things. But as far as the asteroid redirect mission, no problems, or even the sample return from it.
Yeah, it will help. I think one thing that ARM will do is help that discussion along and that progression. Because one of the goals is to have basically an orbital laboratory in cislunar space with that material that we've returned. And my hope is that we will have international and commercial companies go to it and start learning how to process with telerobotics and short comm delays. So I think there's a lot of benefits there, but it's gonna introduce, it's gonna kind of beg the question of what
The ownership piece will be
ownership and-
something. If you went up to an asteroid first and started setting up an equipment that would keep processing the mineral, the ore, as it orbits, and then someone goes up and takes it before you got to it. Now that's piracy. How does that fit in the law? Or, this is a good one I'm fascinated with. I look at environmental management and hazard management. So asteroids are a natural hazard, and they hit. It's the only natural hazard you can totally prevent. Not just mitigate, like you can build a levee and keep the flood out. You can give people hurricane warnings and stuff. This one, you can turn it into a non-event. Or, if you make a mistake, you've turned a natural hazard into a human-caused hazard. And so there are some legal things that are fascinating to look at, really neat. But internally, no problem. Exploration, problem. Sample return, no problem at this point. Ownership of the rocks in a land, so the ownership, could it be the state or the government? So the stuff that falls on Australia is Australian. Stuff that falls here is ours.
And interestingly, after the crewed mission is over, and the robotic spacecraft goes in its parking orbit there for a few hundred years, the sample still belongs to somebody, not just the robotic spacecraft, but that particular rock. It still has an owner. Well, it has to. Yeah. Oh yeah, and whatever.
Spacecraft owns the rock.
So this was just to.
So when the Google Lunar X Prize was talked about and said when you go there you don't want to have people taking things, and the spacecraft itself is owned by the launching nation. And so Google Lunar X and NASA together said, okay, you kind of put a circle around them and don't let people destroy these human heritage sites. And one of the lawyers said to me, who said they can put a circle around it? They don't own the land that the spacecraft is sitting on. So there's all sorts of things.
Okay. Thank you, everybody. This was a lot of fun.